Good afternoon, class. Here's Chapter 4, Application of Derivatives, Section 4.6, Antiderivatives. We've covered maximum and minimum values, how derivatives affect the shape of a graph, optimization problems, and now the last section, antiderivatives. Reminding you of differentiation formulas from definition to power rule, trigonometric functions, product, quotient, chain rule, the derivative of exponential functions, logs, and when you have a curve y equals f of x, delta y is rise along the curve, dy is along the tangent line, dx or delta x are identical, delta y is precisely f of x plus delta x, which is this distance, minus f of x, which is this distance, dy is f prime of x dx. Linearization refers to finding an equation of a tangent line, and I would go with the easy way out. Now, section 4.6, antiderivatives, antidifferentiation, also known as integration. Calculus has two parts. Differential calculus deals with instantaneous rate of change and slope of a tangent line, and integral calculus deals with accumulated change and area under a curve. Both parts rely heavily on the concept of a limit, and they are intimately related. Integral is the opposite of a derivative, also called antiderivative. Question. Given the derivative of a function, what is the original function we started with? That's the idea. All right, so having said that, I'm going to continue. The antiderivative of lowercase f of x is the set of function capital F of x plus c such that d dx of capital F of x plus c is lowercase f of x. The constant c is called the constant of integration. Antidifferentiation is often called integration. Now, understand, when you differentiate, you get one function. When you anti-differentiate, you get a family of functions, because if you differentiate a constant, you get zero. That's why it's a family of functions. So having said that, to indicate the antiderivative of x squared is x cubed over 3 or 1/3 x cubed plus c, we write the integral, this integral sign, x squared dx is x cubed over 3 plus c. This symbol was introduced by Leibniz and is called an integral sign. It is an elongated S. Think about it. Elongated looks like that. And was chosen because an integral is a limit of sums. In general, the integral of f of x dx is capital F of x plus c. Capital F of x plus c is the general form of the antiderivative of lowercase f of x. If f and g, capital F and capital G, are any two antiderivatives of lowercase f, then capital F prime is lowercase f of x, capital G prime is also lowercase f of x. What does it mean? The two functions are the same except with a constant. That means one is the sum of the other one and a constant. G of x is f of x plus c, or you can say capital F of x is g of x minus c. Makes no difference. So their difference is just a number. Let's get started with warm-up examples. Determine these indefinite integrals, that is, find the antiderivative of each integrand. The integral of 8 dx. Concentrate on 8. What is it that I differentiate to get 8? I hope you realize that's 8x, so we're going to add a constant. And the importance of dx, by the way, if I had the integral of 8 dt, then I would have to write a t plus a constant. So dx tells you what independent variable you use. Now, if you recall when we learned division first, we would try it and check it with multiplication. So the reverse process. So we are going to check our work, differentiate the right side, and you do get 8. What about the integral of 10x to the power of 9 dx? Think about a function. You differentiate, you get 10x to the power of 9, and that would be x to the power of 10. Therefore, we add a constant. To prove we haven't made a mistake, we're going to differentiate the right side. And it does give us 10x to the power of 9, of course, without the dx. When you differentiate, it gives you the answer without the dx. Now, e to the power of x, as you know, the derivative is itself. So the answer is itself plus a constant. So to check, you differentiate the right side. And finally, 1 over x, as you recall, 1 over x dx. As you recall, the derivative of natural log is 1 over x. So you're going to say natural log of absolute value of x plus c. And again, absolute value because the domain is from 0 to infinity. You check by differentiating the right side. So it's pretty straightforward, everybody. Now, what is the derivative of kx? Is k. K is a number, is a constant. So if the derivative of kx is k, then the integral of k times dx must be kx plus c. That's actually the proof, believe it or not. What about the power rule? We know the derivative of x to the power of n is nx to the power of n minus 1. What should be the integral of x to the power of n dx? The reverse process. Remember, what do we do to get to the derivative? We multiply, n becomes the coefficient, we multiply by it. So over there, we have to divide. And the exponent goes down by 1, over there has to go up by 1. So in this case, the integral of x to the power of n dx must be 1 over n plus 1, x to the power of n plus 1, and a constant. Needless to say, n can't be negative 1. Now, let's look at this from the point of view of the process by which we differentiate. Number 1, we multiply by n. Number 2, we subtract 1 from n. So these are the steps, 1 and 2. Now, to integrate, we are going to reverse the process. To reverse the process, we're going to go this one, and this comes first. So number 2, subtract 1 becomes add 1, the reverse process, to n. Multiply, now divide by n plus 1. So I hope you see that works. Also, we can easily prove it by simply differentiating this piece. If I want to differentiate this, what do I get? 1 over n plus 1 times n plus 1, x to the power of n plus 1 minus 1 plus c gives me 0. I hope you see that this is x to the power of. So that's an easy proof. What about this? Let me erase my work and we look at them one by one. If the derivative of e to the power of x is e to the power of x, then the integral of e to the power of x dx must be e to the power of x and a constant. If the derivative of natural log is 1 over x, the integral of 1 over x dx must be natural log and a constant. If the derivative of sine is cosine, then the integral of cosine x dx must be sine x plus c. Now, I want you to pay attention to this because it has a negative sign. So class, you could say, take a look, the integral of minus sine x dx is positive cosine x and a constant. And that's right. But you don't want to take the integral of negative cosine x. Let's take the integral of positive sine x. And I hope you see if I have positive sine x, this must be negative. Therefore, the integral of sine x dx is minus cosine x plus c. So when you have a negative, when you differentiate, you put the negative on the other side, okay? When you integrate. So because you don't want to integrate minus sine x. Needless to say, the integral of minus sine x dx is positive cosine x plus c. And having said that, The integral of sine x. You can multiply both sides by negative this because minus cosine x. And this is a constant class. This is just some number. Let me erase my work. What about this one? If the derivative of tangent is secant squared, then the integral of secant squared dx must be tan x plus c. If the derivative of cotangent is negative cosecant squared x, then the integral of positive cosecant squared x dx must be negative cotangent x plus c, just as we discussed it here. Secant gives you secant x tan x. So the integral of the right side, secant x tan x dx, must be secant x and a constant. And this one is negative. So the integral of positive cosecant x cotangent x dx must make this one negative, minus cosecant x and a constant. Those are pretty obvious. Now, as far as having a multiplier, a coefficient k, k is a number. When you differentiate or integrate, it just remains. It doesn't go away. So you can keep it inside or outside the integrals. Sum and difference rules. When we differentiate or integrate, we do term by term. That's really the meaning of sum and difference. If the derivative of e to the power of kx is itself times k, then the integral of e to the power of kx must itself divided by k. So the integral of e to the power of kx dx must be 1 over k e to the power of kx plus a constant. So it's pretty straightforward. All right, let's start here. The integral of x to the power of 7 dx, and I'm going to remind you the integral of x to the power of n dx is 1 over n plus 1, x to the power of n plus 1 on a constant. That is known as the power rule. So we're going to add 1 to 7, and we're going to divide by that and a constant. So x to the power of 7 plus 1 over 7 plus 1 and constant. We rewrite it. We are done. What about x to the power of 99 dx? The same thing. Add 1 to 99 and then divide by it and a constant. So when you add 1 to 99, you get 100. So 1 over 100, x to the power of 100 and a constant. What happens here? Just as we did with the differentiation, we would make it for the power rule by rewriting it. This is algebraic technique, x to the power of 1/2 first. Now, following that, we're going to add 1 and we're going to divide by it. So 1 over 1/2 plus 1, x to the power of 1/2 plus 1, and a constant. This is 3/2. 1 over that is 2/3. So 2/3, x to the power of 3/2, plus a constant. Same thing here. If we wanted to differentiate, we wouldn't. We would make it ready for the power rule. For integration, we make it ready for the power rule. We write it as x to the power minus 3 first. And now, 1 over negative 3 plus 1, x to the power of negative 3 plus 1, and a constant. This is the only calculus step. In fact, this is the only calculus step. This was algebra, the rest will be algebra. So, a negative 3 and 1, okay, negative 2. And this goes down, so the final answer, minus 1 over 2x squared plus the constant. As you can see, the calculus step is really fairly easy, not a lot of calculus steps. Exponentials, remember the derivative and the integral of exponential, the answer is itself. However, in the case of differentiation, e to the power of kx, we multiply by k. In the case of integration, we divide. So the answer is itself, e to the power of 4x. Because we are integrating, divided by 4 and a constant. So we write 1/4 of e to the power 4x and a constant. What about this one? Again, the answer is itself. But we are integrating, we're going to divide by -3. So 1 over -3, or simply -1/3, e to the power -3x and a constant. What about this one? First, let's rewrite it, because in case somebody can't see what's going on, we're going to write it as e to the power 1/2 x. In other words, the coefficient of x is 1/2. So the answer is itself, but divided by what? 1/2. 1 divided by 1/2 is 2. The final answer is 2 e to the power of x over 2 plus c. What about here? Again, we may not recognize this. Therefore, we are going to rewrite it as 2 times 1 over x. 2 remains, and 1 over x, we know the answer is a natural log. So 2 natural log of x plus a constant. We put an absolute value unless we know x is positive. So you rewrite it to make sure we don't make a mistake. What about this one? Again, we're going to rewrite it. It's 1/2 times 1 over x. And again, 1/2 remains. This is a natural log. So 1/2 ln of absolute value of x plus c is the final answer, everybody.